Hello guys, good morning. So you have one, two, three of you. Okay, wait for 2 more minutes. Okay guys, we'll start. Let them join. Share my screen. Okay. So we saw so many things yesterday. So we'll just have a quick recap of what we saw. Okay, so I think this is what we were seeing, right? So this is addition of water molecule, right? So I told you first H plus, then H2O, then H plus leaves. So again, you have a carbocation. Rearrangement is possible. So this is the case of NOCl, right? Nitronium chloride, it's called nitronium ion. So again, NO plus attacks first, then your Cl minus. Now here I don't have the case of syn and anti because you can have bond rotations happening. Say the single bond rotation can happen. So here syn or anti doesn't matter much, right? But if I go for this reaction, right? If I go for Br2, right? Here I will be getting only anti product, right? No chance that I'll be getting syn product because of the mechanism, right? So first Br2 will undergo heterolytic cleavage to form Br plus and Br minus, right? So this Br plus first attacks, now you will form a cyclic bromonium ion, right? The cyclic structure you can see here, and then the Br minus attacks from the opposite side because down you have the Br. So again, it cannot come from the same side, so it has to come on the opposite side. So you'll always end up with anti product. So this is how the product will look, right? And then if you have in the same reaction medium, if you have some other nucleophiles present, instead of Br minus, you have Cl minus H2O. If you have those stuff, you will get products accordingly, right? So you have Cl here, you have OH here. One Br is definitely there because that Br plus is one is going to attack first, right? Okay. Then we went on to see how to form an epoxide. Guys, this is very important. I wanted to include one point here. There is some there are some specific peroxy acids we'll use. So sometimes you will see the reaction medium, they'll not give you peroxy acids, but they will give something like MCPBA. Right. So they just give the instead of peroxy acid here, they will just give this. Now, what is this? It's metachloroperoxybenzoic acid. Right. So if you look at the structure, it's pretty easy, right? Say I have a benzene, right, and a peroxy acid. So I'm going to have C double bond O. If it's OH, that's just OH is normal acid. I just have to put OH, right? And obviously a benzene ring. In the meta position, I'm going to have a chlorine. So this is what is called as MCPBA, right? So whenever you're going to add peroxy acid, to C double bond O, right, you will be ending up with epoxides. So these are the structures for epoxides, right? Okay, so that this one point to remember, guys, is very like in this last year JE also I got a question from this, right? They gave an alkene and they gave MCPP. You just have to make sure that you're going to form an epoxide. That's it, right? Okay, so then we went on to see, yeah, then we went on to see almost like oxidation reactions now, right? These are still addition reactions, but I can call it oxidation because of the mechanism, like how it's happening, right? So first one is the Bayer's reagent. We know what is Bayer's reagent: cold alkaline dilute KMnO4, right? So here you see the mechanism. You'll always end up only and only with syn diols, right? Because of the mechanism, you can see how the mechanism goes, right? Same reaction can be brought out by OSO4, osmium tetroxide, right? So again, it is going to give me syn product, right? Okay, the next one was most important one, that was ozonolysis, right? So I told you just break the double bond, put oxygen both sides. So I told you how to practice something. We even did a good problem on this, right? So now ozonolysis, the next one would be the opposite of Bayer's reagent, that is hot concentrated acidic KMnO4, right? So here you are going to do exactly what you did in case of your ozonolysis, but in ozonolysis you see that you can have either aldehydes or ketones as a product, right? Now ketones cannot be oxidized, but aldehydes can be oxidized to acids, right? So if wherever you form an aldehyde, there you have to end up with an acid, and ketones will stay as such, like in the case of your hot acidic KMnO4, right? Okay, so you can, these are the reactions. You can see one aldehyde is the end product would be this, right, and this, right? Okay, so that we saw, that is an aldehyde getting converted to an acid. Okay, I think this is where we stopped. I think we just went more. Yeah, here we have, right? So then I said I got I forgot certain things. I forgot about the addition of, say, formation of alcohol from alkenes, right? Say first one was that one hydrolysis, H plus bar H2. Second one would be hydroboration oxidation. In this case, what you have to remember is I'm going to get an anti-Markovnikov's product, and there is obviously no rearrangement because there is no carbocation. And the next one will be oxymercuration democration, right? So you have to use a mercuric acetate, right? So you'll be ending up with again here you have to get Markovnikov's product, but again no rearrangement because there is no carbocation. Okay, right. Now guys, I just have one last addition reaction. Okay, so that alone we'll see, and then we'll move on to the next type of reactions. Any questions, guys? Any questions do you have? Okay, I suppose there are no questions, right? So the one last addition reaction is the addition of carbenes, right? When I have addition of again, addition of carbenes. Now we saw what carbenes are, right? So can anyone tell me what carbenes are, people? Anyone wants to comment? What are carbenes? Whatever you know about carbenes, just let me know.
Carbon diradical.
Okay, carbene is a diradical. Good. It is an intermediate, isn't it? Right. So you will have some structures like this. You have as carbon, and you have two other bonds. It can be hydrogens, HH, or it can be even alkyl groups, but you have a diradical here, right? So that is structure for carbene. Okay, so I think you will be able to predict what kind of product I'm going to get. It is just like how I'm going to add your peroxy acid, is it not? Right? Say if you have, one second, guys. Right. So if you have a C double bond C, oh God, wait, guys. So if you have, oh, why is it happening? So if you have a C double bond C, okay. Now, if you put a carbene, now how and all you can synthesize carbene is pretty simple. There are structures like this. Say if you have a CH2 twice S, right? So you have certain molecules like this. So guys, whenever you mention the CH2, wherever you see it, right, you will just understood that it is going. I'm going to get a carbene. So obviously you have to heat it. Okay, so you'll be ending up with CH2 double dot. Okay, now this is gonna go here. Now I think again this pi bond will undergo homolytic cleavage, right? Okay, so obviously you can see one radical here, another radical will form a bond, another radical here, and this one is going to form a bond. You'll always end up with a cyclopropyl ring. One second, guys. Okay, so oh, the double bond is not there. So here you have H and another H, right? So this is a common structure. Again, this H can be alkyl groups also, right? So this is a very common thing, right? That is, you are going to form a cyclopropyl ring. So if I have to draw it properly, I can draw it like this. I mean, you do not necessarily hydrogens, right? So I can just okay, and this again will have, oh god, this is irritating, guys. Wait. Okay, anyways, this is the structure. You'll always end up with a cyclopropyl group if you add carbene to a double bond, C double bond C. Okay, so this is one last addition reaction which you have to know. So you saw how many addition reactions we saw with respect to alkenes, right? So again, if you go for nucleophilic addition with respect to C double bond O, again, I'll have different mechanisms, different kinds of reactions which can happen, right? Okay, so that's about the addition reaction, guys. Right, now we'll move on, right? We'll move on to elimination reactions. So first, hope you understand what and all we saw. We started with um, free radical substitution, and I even saw free radical addition, right? Then we went on to see the addition reactions. Now we are seeing only electrophilic addition, right? Nucleophilic addition will take up when I have C double bond, those carbonyl compounds coming, right? So now we'll move on with your elimination reaction. Okay, now I think we'll understand from the name what you're going to do here. You're going to eliminate a group of molecules. Say it can be H2O, it can be HCl, it can be anything. And I'll just tell you what are all the possibilities. But first, you have to understand what are the ways in which elimination can happen. Okay, right now there are how do you have for substitution reaction, nucleophilic substitution, you have SN2, SN1, all these things you have. Just like that, I have for elimination also. Okay, right? So we'll see what happens there, people. Right, I'll first give you an example, then maybe we'll move on. Say for example, if you have CH3 CH2 Cl, and if I go for alcoholic KOH, right? So we know what we're going to end up with. We are actually going to end up with CH2 double bond CH2 plus, you're going to get HCl eliminated, right? Fine. So this is one of the reactions. Say I can even have dehydration reactions happening, right? Say something like this. If the same thing, if I have CH3, CH2, OH, and if I go for any dehydrating agent, right? So dehydrating, one of the examples can be concentrated H2SO4, right? So again, you'll be ending up with alkene, but this time the eliminated molecule is going to be water, right? So this is like this is the elimination reaction. So you want to eliminate a molecule from the substrate, right? Okay. Now we'll look at what are the mechanisms proposed for this. Okay. So we just go on. We will see first what is this. The first mechanism proposed is E2 mechanism, right? Just like you have SN1, SN2, just like I have E1 and E2, and I have one more also. I have something called as E1CV, but again, we see that. So just like how you have SN2, it is very, very, very similar to SN2, guys, right? So hope you know what happens in SN2, right? This is a single step process, SN2. They are talking about SN2. This is also going to be single step process. Okay, let me write down the points. It is going to be a single step process, right? And it is going to follow second order kinetics, the order of the reaction. Hope you remember chemical kinetics. We'll again go to it, don't worry, right? This is going to be a second order reaction. Okay, and this is what you need to know. Now we'll just look at the mechanism, how it exactly happens. Okay, right. So okay, now I'm going to have a carbon with a hydrogen, right? Say other things will be there, and I have another carbon, and I'm going to have one leaving group. So Lg represents leaving group. Okay, right. Now we'll see what happens. Okay, in case of E1, in case of E2, we're talking about E2 mechanism, right? So obviously you are going to have, say, a base. Now the role of alcoholic KOH here, like you saw previous cases, right? Or I can just even actually put OH minus, that would be better, right? Right. Okay. So I have OH minus. That is basically it is. Now this OH minus is not going to undergo substitution reaction, guys. Okay. I want to tell you a point. Okay. Now answer this question. You already know this reaction, right? So this reaction you know already. The alcoholic KOH, if I put, I'm going to get alkene as the product, that I know, right? Now instead of this, if I put aqueous KOH, what will happen? Hey, is there too much background noise? Are you hearing?
Oh, sir, it's fine.
Okay, fine. Anyways, so I'm talking about this aqueous KOH and alcoholic KOH, right? So tell me, what is the difference between these two?
Sir, KOH in water and KOH in alcohol, dissolved in an alcohol.
Definitely, that's the thing. So KOH dissolved in water, that is aqueous KOH, and KOH dissolved in alcohol, that is alcoholic KOH. That is okay. So what will happen if I for this substrate, for the same substrate, if I put aqueous KOH, what will be the product?
Aqueous KOH is used for substitution reaction.
Exactly, right? So you'll see that I have OH minus there. That OH minus is going to replace your
Ethanol.
Cl minus. So you'll be ending up with alcohol, right? That's the thing, right? Now, how is it that I am able to make just by changing the solvent, right? I'm seeing that actually I'm able to get a different product itself, right? Now, how this happens is that in case of aqueous KOH, you have the availability of OH minus ions to be in surplus, right? So much of OH minus ions that it can act as a nucleophile, right? But in alcoholic KOH, right, this dissociation is not going to happen. Actually, it is not going to give me OH minus, right? But what it will act as is that this is going to act as a base. That's what you need to understand. Okay, so this alcoholic KOH is going to act as a base. That means the only role of this base is going to be abstracting a proton from the substrate. We know how bases work. Bases can either give me OH minus or they can accept H plus, right? So the alcoholic KOH is going to act as a base which is going to accept H plus, right? And aqueous KOH is going to act as a nucleophile. That's the basic difference between aqueous KOH and alcoholic KOH. Okay, so they will even sometimes represent it like this: NaOH. Oh God, this is taking so much time. So they'll just write it as NaOH in C2H5OH. So if you represent it like this also, it means it is alcoholic medium. Again, you should not put what is that substitution reaction. You have to go for elimination only. Okay, so that's that you can see this. Whenever I put a bar, this represents the medium. This represents the solvent, or sometimes even catalyst. Okay, this is the main reagent. Okay, so anyways, we are talking about this thing. What is that? Your mechanism for E2, right? Okay, so first what happens, actually there is no first or second. I told you this is going to be the only one step process. Okay, so what is going to happen is this OH minus is going to come here, right? And it is going to take this H plus, right? So you can see the arrow mark. If you put the arrow mark towards carbon, that means H plus is coming out, right? And obviously the leaving group leaves simultaneously. Okay, I'll tell you again. So the abstraction of H plus by the OH minus happens, and simultaneously you are going to have the cleavage of the leaving group and the carbon bond also. This is going to be a single step process, and it's pretty simple. You'll be ending up with an alkene. Pretty simple. Single step process, right? Just like how you have in SN2, a single step process. In that case, you may break one bond and you make one bond simultaneously, right? So the nucleophile, incoming nucleophile and the carbon will form a new bond, and there'll be a leaving group, and the leaving group leaves, and the nucleophile attack happens simultaneously. Now here also it is going to happen simultaneously. The only difference is here I'm going to break two bonds. That's it. That's what you need to know. Okay, so this is what is E2 mechanism, right? And there is just one more thing I want to tell you, right? So here, guys, you have to understand that this hydrogen, right, this hydrogen which is getting eliminated. Actually, I didn't draw the stereochemistry properly, in the sense that I didn't draw the 3D structure properly. But what you have to understand is the hydrogen can be abstracted only if it's only if it is in anti position to the leaving group. That means the leaving group is here, the hydrogen actually should be abstracted from here. So that's what, again, why you can understand, because the OH minus is a strong, like you have large number of electrons there. The leaving group, like say Cl minus, also will have large number of electrons. Actually, the OH minus will prefer to come from this side and take the proton. That's how it happens. Okay, right? Okay, so if I can give you an example properly, that will make some sense. Okay, so say assume that I have a Cl here. Okay, now say there is a methyl group here. Okay, now I have to draw the stereochemistry. Sorry, wait, 1 second. I have to draw the 3D structures properly. Say assume that this chlorine atom is facing away from us. Okay, and say there is a methyl group which is, right, there is a methyl group here, and obviously the other hydrogen atom is like this, right? And there is, say, another methyl group here, and okay, let me draw the stereochemistry also, right? Say the other methyl group here is pointing away from us, right? And obviously the methyl group, oh sorry, the hydrogen here is gonna be pointing towards you. Okay, now guys, think and tell me, right? Say if I just mark the hydrogens as 1, okay, this is 2, this is 1. Okay, now tell me which hydrogen will be eliminated, hydrogen 1 or hydrogen 2? Okay, let me take a vote maybe. Okay, guys, already participate. Just put it in the chat box whether it's going to be hydrogen 1 or hydrogen 2.
Can you show the compound again?
Yeah, sure. Right. Yeah, this is the compound. I think I should draw a better picture, guys. Wait, actually, I will take some space and draw it properly. Wait. Okay. Now there is a chlorine atom which is pointing away. Okay. Now there is a methyl group. Right. This is a wedge, guys. I'll not just shade it. This is CH3. Okay, and there is a hydrogen atom which is pointing away. And here, when I come here, so you are going to have a methyl group pointing away from you, right? And the hydrogen atom here is, sorry, pointing towards us. Okay, now if I mark this hydrogen as 1, okay, this is 1, and if this is 2, okay, obviously Cl minus will leave, no doubt. Now obviously you are going to take the hydrogen from the next atom. This is beta elimination. Please remember, guys, the elimination process we are talking about is beta elimination. Okay, alpha carbon atom is the one which is having the functional group. So this is my alpha. The carbon atom which is having the functional group is alpha. So there are 2 beta hydrogens, or I would say there are 2 beta carbons which are having hydrogens, right? Okay. Now, tell me whether it's going to be hydrogen 1 or hydrogen 2. You can put it in the chat box, or you can even tell me again, you want to see it. Okay, you can see it. Okay, it is going to be just a guess. Okay, Harini says 1.
So 1, sir.
Okay, again 1. Others? Okay, again 1. Come on, guys, everybody participate. Like there are almost 8 people here. I got only 3. What about other almost 5 people left? Okay, Ari says 1. Okay, again 1. Okay, fine. Everybody says 1. I think then you understood what I'm trying to say here. So this is what you have to understand. The hydrogen should be anti to my leaving group, in the sense that you see that the chlorine atom here is pointing away from us, right? So if you are going to abstract an hydrogen, it is better that the next beta hydrogen should be pointing towards me, right? So here you can see the hydrogen atom is again pointing away from us, but this is pointing towards us, right? So if you look at the product, if I put my alcoholic KOH, you will be getting a double bond which is here, right? But if this hydrogen left, you would have got a double bond here. Hope you understand, right? There is a lot of difference between these two. But even though that, say, this is CH3 and this is CH3, now this compound is a little symmetrical, but you're finding it, right? But if it was some other group, this is C2H5, this is CH3, then again you will have some problem there. Okay, right? So this would have been the problem. Obviously methyl groups are there, don't worry. Okay, so this is how it is going to happen. You have to remember that the hydrogen which is anti to the leaving group will be eliminated. That's what you need to understand. Cool, right? And if there is a problem, right, if there's a problem in the sense, if there's a problem of unsymmetry in the molecule, right? So hope you remember there's something called a Zaitsev rule. Okay, Zaitsev rule, you hope you remember. Right? So hope you remember Zaitsev rule, just like Markov-Nichols is for addition reaction, Zaitsev is for elimination reaction. Okay, hope you remember what Zaitsev rule is. You have to make sure that the double bond is formed between the two most substituted carbon atoms. Right? Again, I repeat, the double bond should be formed between the carbon atoms which are more substituted. Right? So how will I give you an example for this? Maybe I'll just go here. Right? Say for example, if you have oops, okay, say if you have, oh god, I have to change my stylus. That's what I need to do. CH3, CH2, CH, Cl, CH3. Now if I go for your alcoholic KOH, right? So now again you can remove this hydrogen or you can remove this hydrogen, but according to Zaitsev rule, you have to remove this hydrogen only because you'll form the double bond between more substituted carbon atoms. So you will get CH3, CH, double bond, CH, and CH3. Okay, so this you would have known Zaitsev rule. Okay, right, again, the reason if you check again, it's because of the okay, why okay, anybody wants to comment on why this reason? Why is it that I go for a more substituted alkene? Any idea, guys? It is not because of carbocation, because carbocation is not formed. It is not because of anything. It's not because of steric hindrance, because if it is steric hindrance, right, obviously abstracting this proton is easier. Is it not? The OH minus can easily come and take this proton because it is not that much crowded. But taking this proton is so much difficult, but still the product is according to the abstraction of hydrogen from this carbon atom only. That is this carbon atom only. Right. Any reasons you want to come up with? It can be a guess. Any reasons which you think of? What can be the reasons for this? Okay, so let me ask you this question: if I give you two alkenes, or say three alkenes, if I give you, right, and I ask you to arrange them in the order of their stabilities, or I would say, in other words, if I put, okay, in the order of stability only, right? I have three alkenes with you, right? I'm asking you to arrange them in the order of stability. What is the criteria you will use for arranging them in the order of their stabilities? Do you have any criteria? Do you have any rules which you know? Anyways, I'm going to tell you the answer. I'm just asking you. Okay. So I suppose no one knows. So guys, please remember, when I go for stability of alkenes,
Sir, is there a possibility of resonance?
yes, that comes into the picture. I'll tell you. When I have a conjugated diene or conjugated system, yes, there's a possibility of resonance, right? Okay, so when I go for hey, what is wrong? Stability of alkenes, right? So please remember this, right? So when you have a conjugated system, okay, a conjugated system is more stable, right? When obviously, when you hope you know what is a conjugated system: double bond, single bond, double bond, alternating double bond, just like how you have in benzene, right? So conjugated systems are more stable, more and more conjugation, more and more stable. So if I give you two conjugated dienes, right? So whichever has more number of alternate double bonds is going to be more stable. So more conjugation, more stability, right? Next one is when you don't have conjugation, right? So then you go for more substituted alkenes, right? You go for more substituted, oh god, okay, more substituted alkenes. And even like this is substituted alkene, right? This is more bulky, right? This side you have substituent, this side you have substituents, right? And at last you have non-substituted, right? Lesser bulky ones. Oh god, I think I really have to change me. Sir, please bear with this, guys. Even I'm getting irritated. Right, the lesser bulky ones, right? So when you have conjugated systems, that is going to give me the maximum stability. Then if you don't have conjugation, go for more substituted ones, and your last least stable would be the one which are least bulky. Okay, right? So this is what you need to know. So you can see this according to stability of alkenes only, I'm going to get the product here, right? So it is not because of anything else, it is just because of stability of alkenes. Substituted alkenes are always more stable than non-substituted alkenes. Okay, right? So I have to remember two things about E2 elimination. One is that you have to follow Zaitsev rule. Second one is you have to abstract the hydrogen which is anti to the leaving group. These two things you remember, you're set. That's it. Okay, so that is about E2. Sorry, E2, right? So again, if I look at the order of if I look at the what to say, if I have primary, secondary, and tertiary chlorides, right? Alkyl chlorides, which is going to react most. Again, it's exactly going to be same as in the case of SN2, right? Now, what do you think will be the reactivity? Primary, secondary, and tertiary, which will react the fastest in E2? Primary, secondary, tertiary alkyl chlorides, if I have, which will react the fastest with respect to E2? What happens in SN2? In SN2, primary, secondary, tertiary, which reacts the fastest? Whoa.
Primary.
Thank you so much. Right. So obviously it's primary, right? So you can see that two things are happening simultaneously, right? So obviously a lesser bulky substrate will react faster. Okay. So with respect to primary, sorry, with respect to E2, the order of the order of reactivity will be primary will be the most reactive, the least reactive would be tertiary. That's what you need to know. Okay, primary, secondary, tertiary. This is the order of reactivity, not stability, guys. We're not talking about stability. Again, in this, if you have a problem, like if you have an unsymmetrical case, right, then you have to go for Zaitsev rule and your abstraction of H plus from the anti position, right? So this is for E2 mechanism. Okay, right, fine. Now let me move on. We'll move on to see what is this E1 mechanism. So, okay, now what is this second order kinetics? Tell me, where is this? Now tell me, I told you that it is a second, it follows second order kinetics. What do you mean by this?
The rate of reaction depends upon the concentration of two reactants.
Which two are the reactants here?
The base and The
The
alkyl
substrate.
chloride.
Okay,
Yeah.
understood. Yes, absolutely true. Right. So whenever I say second order kinetics, guys, hope you know how to write the rate law equation. So you will write R is equal to K into A power X into B power Y. The sum of X plus Y is what is called as the order of the reaction. Right. So if I have to write the rate law for this, R will be equal to some rate constant K right, some rate constant K into the concentration of the substrate. Right, the concentration of the substrate and the concentration of the base, both to the power 1 and 1 and 1. Right. Okay, so that's why the overall order is 2. That's what we need to know by second order kinetics. Okay, fine. So we'll move on to E1 mechanism. Okay, so you can see it is going to be a two-step process. Right, and it is going to follow first order kinetics. Okay, right, that means it is going to depend only on one of them, not both of them, right? And the one which is going to depend upon is the substrate and not the base. The base concentration doesn't matter here. I have to look at only the substrate concentration. Okay, only substrate concentration is important. The other one is not important. Okay, so just like how you have in SN1, right, you have an intermediate there, obviously the carbocation. Here also I'm going to have a carbocation form, right? So obviously if you have E2 there is no question of rearrangement, guys. But if you have E1, there is definitely a possibility of rearrangement. Please be very careful. Okay, so anyways, we'll move on. So we'll see how the mechanism goes. Okay. Okay, I have hydrogen and I'm going to have a leaving group. Wonderful, right? Now, first step, what happens is the leaving group leaves, minus leaving group. Okay, that's the first step. So when the leaving group leaves, obviously it is going to take the electron pair along with this. Okay, so you will be ending up with a carbocation, right? And obviously there is still the hydrogens left. Okay, right? Then what is the next step? Then the base comes, OH minus comes, right? Now this is going to abstract this proton and you will be ending up with C double bond C. Okay, that is completely all right. Okay, so you can see what are the two steps. First step is the leaving group leaves and formation of carbocation. Second step is the abstraction of H plus to make an alkene double bond. That's a two-step process. Okay, now here there is no question of what is that, the hydrogen should be anti or sync to it, because you see the first step is not, it is not going to be a simultaneous process, right? So after the formation of carbocation, the hydrogen can either be here or the hydrogen can even be at the top. It doesn't matter, right? So here the syn or anti doesn't play a role because you form a carbocation which is planar, right? So it really doesn't matter, right? Okay, so that one thing I have to do, but Zaitsev rule stays. E1 Zaitsev rule has to be followed, no doubt. Oh God. Okay, Zaitsev rule has to be followed, right? And again, if you look at the order of reactivity, obviously you see that there's a carbocation formed. So obviously the order of reactivity would be tertiary more reactive than secondary, and secondary more reactive than primary. Okay, right. Now let me give you a question. Let me see if you can get the product. Wait, There was one beautiful question I saw somewhere. Let me think of it. Let me think of the structure first. Okay. Hmm. Okay, where I had it. I forgot the structure. It was a beautiful question. That one involves a lot of rearrangements and stuff. Okay, no issues. Like, we don't have to spend so much time on that, right? So if I have to give you a rearrangement question, I can give you. So say there's a OH here, right? Now I go for concentrated H2SO4. Okay, now tell me guys, what will be the product? Guess the product. Assume E1, obviously. And you have to assume E1 only. Okay, now why is it like this? I'll tell you, right? Because, okay, now the dehydration of alcohol is actually a very good phenomena, guys. Like, okay, first you do this, assume that it is E1. Okay, I'll tell you what happens in alcohol. Don't worry. So assume that it is E1 here. Okay, and tell me, what do you expect the product to be? Okay, let me add some. Okay, I will add a metal group here also. Please take care of that. There's a metal group also. Okay, fine. Hopefully you should have gotten the product by this time. I gave you, okay, I'll give you 1 more minute. Okay, so fine. So if you would have gotten this as the product, you are absolutely right. How many of you got this? Oh, wait. Yeah, this is the product. How many of you got this? Nobody?
So I got it, sir.
Okay, good. Right. So it's pretty simple. First, obviously, I found out form a carbocation. Then you have to make sure that I'm going to have a ring expansion happening, and then you have to eliminate H plus. That's a simple. And you have to remember that I have to follow Sides rule. That's what you need to understand. Okay, cool. So we'll see what happens. Maybe I have to make some space for this. Okay. So, okay, guys, like generally, what happens is the dehydration reaction, that too, if you use, depending on what dehydrating agent you use, right, the alcohols can undergo either E1 or E2. Okay. So generally we use only concentrated H2SO4. Okay. So let me tell you how this happens. Okay. So first the H plus comes. right? First the H plus comes, it is going to attack the lone pair on oxygen. Okay, so what will happen now? I will have OH2 plus, right? And obviously this H2O will leave. Okay, so I can write minus H2O. Okay, so and there's a methyl group, yes, right? So you will get a carbocation, and obviously there is still a methyl group left. Okay, there is a methyl group still left. Okay, so obviously now I have to make sure that I'm going to have ring expansion. Okay, so because it can become a 6-membered ring, so what are the choices? Either you can make this carbon atom attach with that carbon atom, or you can make this carbon atom attach with this carbon atom. Basically you're going to break the bonds, right? Okay, so we'll see what happens, right? Okay, let me do both the structures, right? Okay, so let me break this bond. Okay, if I just draw it in some other color. Okay, let me break this bond. Oh, wait. This bond I'll break. Okay, so fine, if I break that bond, we'll see what is there. Okay, this bond is not there. I have a bond down, another bond, and there is a methyl group, and there is a carbocation. Okay, now you can see that you are going to make this carbon atom attach with this carbon atom, right? So you will see that this attacks here, right? And you, okay, guys, I should draw a better structure, right? Okay. Okay. Now this has something like this. Now you have a carbocation on this, right? But this is going to get attached here, right? Now where will I get the carbocation? The carbocation, this is the carbon atom which doesn't have anything. This and a methyl group, right? So if I draw it properly, this one, a 6-membered ring, right? Let me put the methyl group as my reference, right? So methyl group is here. The next carbon atom, this is the methyl group. The next carbon atom is having a positive charge, right? And you can see the next carbon atom, the carbon having the positive charge, the next carbon atom is having a methyl group also. So the next carbon atom is having a methyl group, right? So now obviously you have to remove H plus from either this, I have a hydrogen here, right? Or I have a hydrogen here. Now either of them you remove, you're going to get the same product. Doesn't matter. Okay, right. Now let me break the other one, right? That is, I'm going to break this one. Okay, basically I'm going to make this carbon atom attach with the carbocation carbon. Okay, so now we'll see what happens, right? So basically I'm going to break this bond now, right? Okay, let me see what happens. So you will have this, this. Now this bond is not there. Now I have a line here, and there is a bond here, right? And now this bond is broken, right? Now I have okay, there's a carbocation here. No issues, right? Now what I'm going to do, I'm going to join these two. Okay, now if I join these two, okay, where's the methyl group? This is the methyl group. This is my reference, right? Okay, so this is the methyl group. Let me draw a structure properly. Okay, so for my reference, let me just put the methyl group here for my reference. Okay, right. Now the methyl group is here, Right. Now, obviously, the carbocation will not be here because this is the carbon atom which has nothing. Like this is the carbon atom which has nothing. Right. So methyl group, the next carbon, methyl group, the next carbon, and the next carbon to that is going to have a positive charge. Right. Okay. Now, next, you can see the carbon atom is having a methyl group here, and the next carbon atom is also having a methyl group. Done. Right. Now, what I can do? Now, this is a primary carbon. This is a secondary carbocation, isn't it? Right. Can I make it tertiary carbocation? Yes or no? Guys, can I make a tertiary carbocation in this? Is it possible? Yes, no, or you don't know? Hello.
Yes, sir, hydrate shift.
Definitely. Right. Yes, definitely. You can have a this hydrogen you have. Oh God, this is really testing my patience. Okay, right. So this hydrogen can be shifted. So now one more hydride shift I do. Guys, I'm doing it very slowly. Like you can see in matter of moments I got the product, but actually there are a lot of stuffs involved. Right. So I go for hydride shift. So you will get the carbocation here. Right. You will get the carbocation here, and there is one methyl group here also. Right. So God. Right. Okay. So you get the methyl group here. Now you have a hydrogen here. Now that is going to get eliminated. So you will see the product is this, the first one. That is the major product. Why? Because you see that is the most substituted alkene you can get in this, right? So if you go for the other one, you can see how the product looks. Where is the product? Oops, where is the product? Oh, I didn't tell you the product. Okay, the product will look like this, guys. Right, I'll tell you the product. This is the carbocation. Again, I can have a tertiary carbocation getting formed here also. I can have the carbocation here, but that is not going to make a much of a difference because whatever you do, you will get. Okay, you will get one actually. Okay, so you have a methyl group here. And you have a methyl group here. So now you will anyways end up with only the double bond here. There is no doubt. Or here, maybe like here in this case, you can even have it here. Anyways, right? You're gonna get even if you do the hydrate shift, even if you're gonna make a carbocation, tertiary carbocation, right? Obviously, the carbocation would have come here now, and you would have had to hide the hydrogen here. That would have gotten. So you will anyways end up with this product, right? But here you can see the double bond is between two methyl groups. The carbonate having two methyl groups. Sides of rule is perfectly followed, but just that you have to do two times rearrangement. Right, one is ring expansion. Like this is how the ring expansion happens. You can see that this bond is broken. Right, this bond. Oh wait, this bond is broken. So you can see then I'm going to attach this carbon atom with this carbon atom. You'll be getting that, and then I go for hydrate shift. So you will be ending up with this carbocation, and then I remove the H plus, and then you will be ending up with this product. Absolutely true. Okay, right? So I hope you understand how rearrangement works. You have to be very careful, and don't worry, we will solve a lot of questions, and you will write a lot of tests. Do not worry about this. Okay. Any questions, guys? Everybody understood? Anybody has any doubt? Anybody didn't understand how the product came or what will be the major product? Obviously, this will be the major product. This will be the major product. Okay, any questions, guys? Do you have any questions from this problem? Okay, I hope everybody has
Sir, but we
clarity.
got the other structure down.
Yes. Okay, so give me a moment. Yes. Can I ask it out? Yes, tell me.
Sir, but we got the other structure at the bottom.
This one.
What?
One second.
Yeah.
This one, right?
Yes, sir.
You got the other structure. Good. If you got any one of the structure is pretty good, Kanna. Pretty good. Right? But if they
So,
ask you major product, then you have to be very careful. See, always go for the two choices. Whenever you go for ring expansion, there are two bonds you can break. Right? Make sure you don't stop with one. You go for the other one also, and check whether I can get any other product. Right? That is always a good thing to do. Like now, you will feel that it will take some little time, right? But once you become practiced, it will take only a matter of 30 seconds, 40 seconds for you to draw the structures. Okay.
yes, sir.
Right. So yeah, it's good that you got this product, right? But the major product is what is marked. Okay, good effort. Cool. We'll move on, guys. So that's about, we have one more, right? We have an elimination. I mean, E1, E2 is there. And obviously the last one.
Sir, I have a doubt.
Yeah, tell me, Kana.
Sir, in major product, எப்படி ரெண்டு methyl group பக்கத்து கார்பன்ல வந்துச்சு?
Then you can see, right? Okay, major product. I'll tell you, explain you again. Okay, so now what you see here is, here you have a carbon. You basically broke this bond. Okay, so the bond is not here. You can see the bond is not here, but I am going to make sure that this and this are going to attach itself. So that is what is here, right? So the carbocation will not be here now. It's gone. Right, where will be the carbocation? The carbocation will be in the carbon atom which doesn't have a bond, basically this carbon atom. This carbon atom, that means this one is going to have the positive charge. Done. Now what do you see? If I have this as the reference point, this is the reference point. The next carbon atom is having a methyl group. The next carbon atom is having a methyl group. After that, I have a carbocation. That's it. That's how they are together. Understood?
Okay. Yes.
Right. So like if you draw, you will understand. I see, the thing about organic is how much ever I explain, right? How much ever I try to say that this is going there, that is coming here, and all these, unless and until you draw it on your paper, it is impossible for you to understand. Right? I faced this problem because I was so lazy that I will not draw the structures and check. But if you are going to be that, you will also face the same problem. Right? So whenever I ask you to draw it, like have some, see, it is going to be a tedious process initially only. Don't worry, initially only it will be some rigorous process, tedious process. But after a while, after say if you solve some 5 questions in ring expansion, 5 questions on rearrangement, you are set. In 30-40 seconds you'll be able to get the structures out. Not a big deal at all. Okay, right? Any other questions anybody has? Fine. Okay, cool. Oh wait, I have to continue in this only, right? So now let me move on. Last type of elimination. Actually, I thought of finishing more stuff, but I don't know what happened. Yes, anyways, so last type of mechanism in elimination is E1CB. Okay, it's called E1CB mechanism. Okay, so again, for first order, why is it like this? So E1CB, again, it's going to be so again, it's going to be first order. right? Okay, so first order, because it says that it is E1, right? Now this CB represents conjugate base, right? So what is conjugate base, people? What do you know about conjugate bases?
Remove the H plus
Yeah,
of the
remove the
compound.
H plus. Yes, yes, absolutely. Remove the H plus. Whatever is remaining is what is called as my conjugate base. Say, for example, HCl, Cl minus is my conjugate base after removing H plus. Say for H2SO4, HSO4 minus is a conjugate base, like that. So after removing H plus, whatever is remaining is what is called as my conjugate base, right? So I think now you will be able to understand the mechanism also, right? Maybe you'll be able to predict the mechanism, and maybe I suppose, okay, we'll see how it happens, right? So I have a hydrogen and a leaving group. Okay, now first, what happens is, now last time in E1 mechanism, what happened? The leaving group left first, formation of carbocation, right? Now here what is going to happen is, first the base comes, right? The base is going to, like, okay, I'm drawing OH minus, but need not be always that. But anyways, so first the base comes, it is going to take the H plus, right? So tell me, no, you don't tell me. You can easily see that you are going to have a carbanion as an intermediate. Okay, the carbanion as an intermediate because H plus left, right? So H plus left, this is my conjugate base. I write as CB. Okay, the conjugate base is there. Okay, right. Now what is going to happen? Now the leaving group is going to leave, obviously. So you will have this coming here and the leaving group leaves. Okay, and the leaving group leaves, you will be ending up with a C double bonds, right? So the only difference between E1 and E1CB is that in E1, first the leaving group leaves. In E1CB, first the H plus leaves. That's the basic difference there. Carbocation is the intermediate. Here, carbanion is the intermediate. But this is very rare, guys. This is very, very, very rare process. Right? This is very rare because the things which can have a stable carbanion, generally carbanions are a little unstable. Again, carbocations are also unstable, but probability of forming carbocations are pretty higher, right? Carbanions will be formed. Okay, so carbanions will be formed only when they have very high stability generally. Okay, so this particular mechanism is pretty rare. You don't have to worry about it. Questions coming from this and all is too much. Like, I don't think so, but you have to know, at least they can be theoretical questions from this, right? So they can give 4 choices about U and CB and ask you to choose a statement which is wrong. Like that kind of questions can come, maybe, right? So it's good to know. So these are the things about elimination reactions. Okay, right? So yeah, what else in elimination reaction? Okay, I have to see what are all the different eliminations I can have, right? That we have to see. Okay, so that we'll see now. So for 2 things you already saw, right? One is when you have an alkyl halide, when you put alcoholic KOH, right, you are going to end up with an alkene, right? And second thing is when you have an alcohol and you put a dehydrating agent, you are going to have again an alkene form. But what I have to inform you is that concentrated H2SO4 is not only the dehydrating agent. Other dehydrating agents can be P2O5. P2O5 is a good dehydrating agent. Even aluminum chloride is a good dehydrating agent. But the only difference is here there is no rearrangement. If you use these for the alcohols, there is literally, oh, how the color changed. Oh, sorry. Okay, there is no rearrangement because there is no carbocation. That's what you need to know. Okay, right. Now, other than that, I can have eliminations like this. Say when you have a geminal or a vicinal, vicinal, what is that? Alkyl halide. Say something like this. Say if you have actually this is getting a little out of control. Okay. Try. Okay. Right. Say if you have geminal or vicinal halides, say something like this. When you have CH2Cl and if you have CH2Cl, right? Now there are other reactions like if you just put zinc here, right? What are you going to get? You are going to get the side product, eliminated product as okay, ZnCl2 obviously, right? And what you're going to get is an alkene, CH2 double bond CH2, right? This is one. Again, even if it is going, this is a vicinal dihalide. You know what is vicinal? The next carbon atoms having this. Even if I'm going to have, this thing, what is that? Geminal. That is, if you have it in the same this thing, so something like this. If you have CH, Cl, Cl, CH3. Right now, same thing if you put, you're going to get the same product, right? Zinc if you put, again I'm going to get ZnCl2 eliminated, right? And I'll be getting the same product. Okay, right? So that is about the other elimination. What other eliminations I have? Yeah, so these are pretty much everything, guys. Dehydration, alcoholic KOH, Wesleyan, and geminal dihalides, right? Now tell me, can I have a geminal diol? Can I have a geminal diol?
No, sir, it's highly unstable.
Okay, so what will happen if I have a geminal diol? Like instead of this ClCl, if I have
Sir,
OH, yeah,
does dehydration happen?
definitely. Guys, please remember this, right? This is a very, you can use this for so many conversions also for your school. Remember, two alcohols, I mean, two OH groups on the same carbon atom is absolutely unstable. Okay, so what will you do is that you will eliminate a water molecule to form a carbonyl group. This, irrespective of whatever is there, is going to happen, right? And except that if these two are very strong electron withdrawing groups, if I have two electron withdrawing groups, right, only in that case geminal diols are a little stable, in the sense that there are something called as chlorals. Okay, right, so chloral structure is like this, right? This is pretty okay. This is a little stable under certain temperatures, but again, 99.999% of times, okay, you are going to, the moment you form this, right, you are going to eliminate it to form a carbonyl compound. You don't have to use anything. It just happens on its own, spontaneous process, right? And one more thing also is unstable. When you have, let me make some space. When you have same carbon atom having OH and NH2, right? Again, is going to be unstable. Okay. Now here water molecule is not eliminated. What is eliminated is ammonia. Okay, instead of this 2, if I write it as NH, right? You are not required actually. You are going to eliminate ammonia molecule. So again, you will be ending up with a carbon compound. Okay, so this is a very good trick for using conversions. Okay, so if you start with something, say if you start with an alkene, right? Now I can go make sure that if you go for an alkyne, maybe, right? So if you want to end up with a carbonyl compound, right? Obviously you can add alcohol, you can add water 2 times, make sure that there is OH in the same carbon atom, 2 OH in the same carbon atom, and obviously you don't have to do anything. It will automatically eliminate water molecule to form carbonyl compound. Okay, so this again, this also, if you want to call elimination, yes, this is an elimination only, but not because of we are doing anything. It is going to happen on its own, because it's going to be. Why is it unstable? Because 2 OH groups, so many number of lone pairs, so much repulsions, and that's why it is unstable. Now, if you ask me that question, right? Same goes with ammonia and OH also. I mean, sorry, NH2 and OH also. Okay, right? So these are the different eliminations. What is the time? Okay, guys, I think my stylus is really creating some problems. I'll stop with this for today. Okay, so I have substitution reactions. I don't think I have to take it, because you already have it studied in your schools, right? SN1, SN2, exactly similar to E1 and E2, right? But there is something called as SNAR, that is when I go for nucleophilic substitution in benzene derivatives, right? There are 2 mechanisms there, so that we'll see next class. Okay, and what else? Electrophilic substitution. Now nucleophilic substitution, I'm not going to cover it because it is already covered there, but anyways, we'll do problems on that, do not worry, right? But electrophilic substitution, yes, I will be covering it. Benzene nitration, Friedel-Crafts reactions, all these things, those things I'll cover. And with that, I'll be stopping with hydrocarbons. It's not exactly hydrocarbons, but most of the things we saw about here only hydrocarbons. Okay, and then maybe which chapter you want to start? Equilibrium is okay for you after that? Or do you have anything in specific? So this chapter you can start, something like that. No, don't tell me any 12 chapters. Tell me 11 chapters. Yes, you have anything in specific in mind? Okay, so maybe it's my choice then. Okay, guys, I'll stop with this for today. Thank you so much. We'll meet next week. Okay.
Thank you, sir.
Thank you, sir.
Thank you.